Okay, we're back. We're going to talk about concavity now. Um, Concavity is something you guys were asking about in class because you saw it on a worksheet, I guess, or maybe that AP free response question. Um, so let's talk about it. Concavity deals with how a graph is curved. All right, a graph that is concave up looks like this. It can hold water, while a graph that is concave down looks like this, a sad face or a hill or an umbrella. We can use the second derivative to determine the concavity of a function. All right, so previously we had the first derivative test here. It helped us determine when the function had a local maximum or a minimum. And now we can also, use the what's going to be the second derivative test to determine concavity. All right, so definition of concavity. Let y equals f of x be a differentiable function on the interval I. The graph of f of x, this is the original function, is concave up on the interval if f prime is increasing, and concave down if f prime is decreasing. Let's go back to our very first picture here. All right, so looking at the original function, where do we have concave? Let's look at concave down first. Okay, well, we have concave down through these areas right here. Okay, agree? When we have a concave down graph, that means, go back to what I was just reading right here, that means the derivative is decreasing. All right, well, clearly the derivative, through these parts that I just drew in blue, the derivative is in fact decreasing. And then when the derivative is increasing, this part right here, what happens there? Well, at that point you have a concave up graph. All right. Just to go ahead and mention it, the place where concavity changes from one to another, from either concave down to concave up or vice versa, that point right there is called the point of inflection. All right, let's go back to where we were. Whoops. Okay, so that's the official definition of concavity. We actually don't use that for this rule because there's an easier way to think about it. So we go on to the second derivative rule. Anyway, all right, if the function, start over. If the first derivative is increasing, then the second derivative must be what? Look back at this page right here. If the first derivative, which is this graph, is increasing, what does the second derivative need to be? Well, second derivative is the slope of this graph, right? This is the first derivative. It's the slope of the original function. Well, second derivative is going to be the slope of the first derivative. So where the first derivative is increasing, what kind of slope do you have? Or what does your derivative look like? Well, it is positive. And similarly, if the first derivative is decreasing, then the second derivative must be negative. Thus, instead of using the definition of concavity to determine whether the function is concave up or down, we can use the following test, the concavity test. This is also kind of called the second derivative test. You can refer to it as either one. The graph of a twice differentiable function, y equals f of x, is concave up on any interval where y double prime is greater than 0, and concave down on any interval where y double prime is less than 0. Okay, make sure that you just realize that we only use this test when the second derivative is actually attainable and easy to get. Okay, you don't want to use the second derivative test if it's going to be some horrible messy problem. It's just when it's a nice, easy, clean function. All right, excuse me. The concavity test can be summed up by the following pictures. Yes, these are silly, but I do think they kind of sort of help remember. They don't help understand maybe, but they do help a little bit remember what's going on. Okay, when the second derivative, which is why there are two positives here because it is the second derivative. when the second derivative is positive, you have concave up. If the second derivative, which is why there are two here, is negative, you have concave down. So happy face with the pluses, everybody smiling, versus sad faces with the, I don't know, eyes closed, upset, and concave down. All right, let's see. Example 5. Using the same graph as our previous example, indicate which portions of the graph are concave up and which portions are concave down. Label the points where the graph changes concavity. Well, we just did that just a minute ago on the other one, but we'll do it again here. All right, so we are concave down through this area, and we are concave up through this area, and we change concavity right here. Now, let's go here. The graph of f prime is graphed below. Yes, it is. That actually does match what we graphed back here on our original first paper, you see. So let's look at this. The graph of f prime is graphed below. Label the x value where the graph changes concavity. Okay, so right here where the graph changes concavity, let's come down here. That is this point right here. That is the change in concavity of the original function. Verify this with the definition of concavity as it relates to the first derivative. Okay, well, according to the definition of concavity, the graph of the original function is concave up if the first derivative is increasing, and it is concave down, the red part, if the first derivative is decreasing. So we're good. That works. Sketch the graph of f double prime on the same grid. Notice that the concavity of f changes when f prime something. All right, well, let's figure out what happens. So we're graphing the graph of f double prime, the second derivative. The second derivative is the slope of the first derivative. Okay, so what's the slope through here? It is a negative slope, right? And then at this point right here, what happens to the slope? It becomes 0, so we know it's going to cross the 0 right here, and then we have a positive slope. So we got something that looks like this. Actually, it should be a line. I can't draw a straight line. So it looks something like that. Going back to the question here, when does the concavity of the original function change? Well, the concavity of the original function changes when the second derivative goes from negative to positive. Doesn't have to go negative positive. It could also go positive to negative. All it has to do is change sign. So notice that the concavity of f changes when f double prime changes sign. All right, next page. Find the intervals where the function g of x equals x to the fourth minus 4x cubed is concave up and concave down. Okay, let's see. I'm glad I have more space. You may actually need some more space than your paper gives you. You might just want to turn the paper over on the back and write there. It's not that bad, but it definitely is squished. Okay, so the first thing we need to do is find the first derivative. That's easy. All right. Now, the second thing we need to do is look for the second derivative. So we got 12x squared minus 24x. Okay, we need to find where the second derivative is equal to 0 for what the method we're going to use here. Okay, so we're looking for where the second derivative is equal to 0. Think about right here, this point right here. The second derivative, the blue line, is equal to 0 at that point, and that is where concavity changed, right? Okay, so come back here. What can I factor out? I can factor out a 12x, and I get x minus 2, and so then I have x equals 0 and x equals 2. I'm going to do a sign chart, and this time I'm using my second derivative. Okay, so if I plug values in on either side of the 0 and the 2, I need to remember to plug them into the second derivative. So it's pretty important to write down what you're doing here. The sign chart is never going to be used for grading, and so it doesn't really matter that you write this down, but I promise it does help to keep in mind where to plug values back in. Okay, so let's think about what we've got here. If we plug any number bigger than 2 back into our second derivative right here, we plug any number bigger than 2 in, what do we get? Well, we get a positive number. If we plug any number between 0 and 1 in, between 0 and 2 in, so let's plug 1 in, we would get 12 minus 24. Well, that's a negative number. Now, if we plug in anything negative, we get 12 times that negative number squared. Well, that makes a really big positive. Minus 24 times the negative number, which gives us a positive number anyway. So we're back to positive. All right. Well, there's a couple ways you can think about this. Actually, never mind. I'm not even going to talk about that on this video. I'm going to talk about it in class. But let's just go on to what this tells us here. So we've got positive, negative, positive. This tells us that g, the original function g, is concave up. When is it concave up? Well, it's concave up when g double prime is positive. Okay, so when would that be? It is concave up from, negative infinity to 0 and from 2 to positive infinity. Concavity, they're always parentheses, so you don't have to worry about that. So let's see, g is concave up on negative infinity to 0 and 2 to infinity because g double prime is greater than 0. And g is concave down on 0 to 2, because that's a b, because g double prime is less than 0. Does that make sense? Does it match all the graphs that we've been doing so far? If we have, let's see, have we used that one? We have not even used that function before, so I don't know why I'm saying that. All right, so you can use the second derivative in order to determine concavity when it's concave up and when it's concave down. All right, let's look at the next page. A point of inflection. A point of inflection is a point where the graph of a function has a tangent line, even if it's a vertical tangent line, and where the concavity changes. All right, we primarily are going to think about the point of inflection as some place where the concavity changes. So let's look at these right here, example 8, and see where our concavity changes on these. Well, on this first one, the concavity is up, and then it switches to down, and then it goes back to up. So it looks like it changes somewhere about here and maybe here. How about on this one? Well, you've got concave up through here, and then you have concave down through here. So somewhere in the middle there, you do actually have a tangent line, a vertical tangent line as well. Somewhere about right there is where your concavity changes from up to down. Okay? And then what about this one? Well, this function is actually concave up the entire time. There is no inflection point on this one. Okay? Let's answer a few questions. Since points of inflection occur when the graph changes what? Points of inflection, these points right here, occur when the graph changes concavity, and the graph changes concavity when the second derivative changes from positive to negative or vice versa. Then if we wanted to find the points of inflection of a graph, we only need to focus on when the second derivative equals 0. We don't call these critical points, by the way. They're going to seem like critical points because we're solving for where it's equal to 0, but this is the second derivative, not the first derivative, and these are not called critical points. Okay. All right, let's see. There we go. Let's do example 9. Find the points of inflection of g of x equals 3x to the 5th, blah, blah, blah. So first thing we need to do, well, what is it asking you? Find the points of inflection. What it's really asking you is where does g double prime change signs? Because if we can figure out where the second derivative changes signs, we can figure out where the original function changes concavity. And if you can figure out where it changes concavity, then you know the point of inflection. All right, so let's see here. The first thing we need to do is find our first derivative. So g prime of x is equal to 15x to the 4th, whoopsie, plus 40x to the 3rd plus 15. Second derivative is, what's that, 60x cubed plus 120x squared. Okay, we're trying to find where g double prime changes sign. So we need the zeros of the second derivative because that'll give us our numbers for our sign chart. All right, so we get 60x cubed plus 12x squared equals 0. What can I factor out? Oh goodness, let's see. I can factor out a 12x squared. I think that's right. And I end up with 5x. Is that right? 5, that's right. Plus 1. Something's wrong. Oh my goodness. Okay. Do you see what I did? When I multiplied 40 times 3, I wrote down 12, not 120. I think I said 120, but anyway, let's fix that because that does quite change the problem. Sorry about that. I'm sure you guys were just waiting on me to find my error. I can imagine how annoying that was. All right, so anyway, what can I factor out now? Let's see. Oh, well, gee, I can factor out a 60x squared this time. So I end up with x plus 2. So my zeros are x equals 0 and x equals negative 2. All right, so I need to make my sign chart. This is my second derivative sign chart. I got negative 2 and 0. Many ways you can do this. You can look at each individual factor, which would be 60 and x and x and x plus 2. All right, 60 is always positive. X is going to be positive at greater than 0. Oops, I'm sorry. And then negative from negative 2 to 0. We're just looking at the x value, just x. So obviously x is negative when x is negative. And then we get positive, negative, 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 negative. X plus 2, what does that give us? It gives us positive in this interval, and then between negative 2 and 0, if I put a negative 1 in here, I still get a positive value. And then after that, I get negatives. Okay, so to the left of negative 2, I have a positive times a negative times a negative times a negative. That gives me a negative. Between negative 2 and 0, I get positive, negative, negative, positive, which gives me a positive. After 0, I clearly have positive values. Okay, so how do we sum this up and answer the question that we were asked? We would write something along the lines of g double prime changes sign Where does it change sign? Well, it only changes sign at one place. It only changes sign at negative 2. And it changes from negative to positive. G double prime changes from negative to positive at x equals negative 2. Therefore, there is a point of inflection at x equals negative 2. because the second derivative changes sign. If the second derivative changes sign, let's go back to this. If the second derivative changes sign, which it does right here, then there is a point of inflection on the first function. All right, last page. Well, maybe. No, it's not actually the last page. Okay, we're getting close. All right, second derivative test for extrema. Actually, I'm going to stop here because I'm afraid I'm getting too long, and I'm going to save another video, so I hope this is not bugging you, but this is kind of a long lesson. Come back. Nope.